next topic is reflection of plane wave at oblique incidence. So what is the oblique incidence? So let's write the oblique incidence definition and how do we define the oblique incidence for the two different type of polarization. As we have studied the normal incidence, and in normal incidence we derived the formula for a reflection coefficient and a transmission coefficient. Similarly, we have to derive here also the formula for reflection coefficient and how to write the wave equation and how to calculate the transmission coefficient. So first of all, we will write the definition of plane of incidence, because the oblique incidence is also known as plane of incidence. So oblique incidence is also referred to as plane of incidence. So plane of incidence is defined as plane containing propagation of incident wave plane containing propagation of incident wave and unit normal vector to the boundary. Unit normal vector to the boundary. I will explain this thing later on, but for time being just try to understand that what is the meaning of this. The meaning of this is nothing but you have to consider a plane in which the wave should be incidenting, and that plane should also have a unit vector normal to the boundary. So obviously there will be a interface or a boundary which separates the two regions, because then only we are having the reflection or transmission. So whenever there is a two medium and there is some interface or the plane which is separating the two medium is called boundary. So here we are saying that a plane should be there, and the plane can be drawn in the 2D, that means on the paper or on the board. I will say on the board, if I will draw the figure in such a way that the plane wave which is traveling is lying in the board and also it contains the unit vector normal to the boundary, will be called as plane of incidence. So there are two types of plane of incidence. There are two types of oblique incidence. First one is parallel polarization. And the definition of parallel polarization is if electric field of uniform plane wave is parallel to the electric field of uniform plane wave is parallel to the plane of incidence, it is called parallel polarization. Just note it down, because I will explain everything in detail. Just I am telling you the basic definitions. So there are two types of oblique incidence. First one is the parallel polarization. If the electric field of the uniform plane wave which is traveling in the plane of incidence is lying or is parallel to the boundary, or is parallel to the, in fact boundary I should say, is parallel to the plane of incidence, it is called parallel polarization. Okay. Now the second one is perpendicular polarization. If the electric field of uniform plane wave, is perpendicular to the plane of incidence, it is called perpendicular polarization. So this is the definition of oblique incidence, that is plane of incidence, and their types. Now we have to define all these things. So let's define that, and for that we have to consider first a plane of incidence, or any plane wave should always satisfy the Maxwell equation. So it should also satisfy the Maxwell equation. So the Maxwell equation for a plane wave is curl of divergence of E is equal to 0, divergence of H equal to 0, curl of E is equal to minus j omega mu H, and curl of H is equal to sigma plus j omega epsilon E. So the oblique incidence which we consider is actually based only for the lossless medium. So we will not be having any loss in the medium, so that means the sigma will be 0. So oblique incidence is considered only for sigma equal to 0. So when we put sigma equal to 0, this Maxwell equation is j omega epsilon E. Now since the plane wave is traveling in the plane of incidence, it is having a propagation vector, that means it is lying in the plane itself. So that means there may be a vector quantity, that is incident propagation vector, that is the reflected propagation vector, or the transmitted propagation vector. So in terms of propagation constant or propagation vector, these Maxwell equations are modified, and that Maxwell equation should also be satisfied in case of oblique incidence. So if I write in terms of propagation vector, so Maxwell's equation in terms of propagation vector is k dot E equal to 0. So delta, that divergence should be replaced by, or the del operator should be replaced by propagation vector k. So k dot H should be 0. For any wave, this condition should be satisfied. So when you writing the electric field or magnetic field for a plane wave which is traveling or reflecting with the oblique incidence, you can consider this equation to be satisfied always. And this is k cross E is equal to omega mu H, and the complex conjugate of this, and k cross H, here we have, if I take complex conjugate, then minus omega epsilon E. This J will be replaced by minus J, and that is only the magnitude part you can remember like that. This is the procedure to remember. You can derive this Maxwell equation also, but there is no need of such derivation. That's why I am not considering here. So this Maxwell equation should be satisfied for a wave to be a plane wave in oblique incidence also. So now we are about to define the oblique incidence. So let's consider a boundary. This is a medium 1 and it is medium 2. So the boundary which is separating these two is Z. Z equal to 0 plane, I am saying. Z equal to 0 plane. So that is Z equal to 0 means you can write XY plane. So there is a XY plane which is separating these two medium. So that is the plane wave which is separating the two medium. Let's write like this. Suppose this is the plane and this plane is separating the two medium. So this is the boundary and left of this boundary we are having medium 1 and to the right we are having another medium. So this is the boundary which is separating the two medium, and normal to the boundary, because this boundary we have considered as z equal to 0. So this is a plane which we have written, which we kept like this. You can kept like this. If you kept like this, then this will be the medium 1 and this would be the medium 2. But here the plane is this. This is the plane we are writing, keeping like this, and this plane which is defined as z equal to 0 is the boundary which is separating the two medium. That means from here, from that side, if I am saying that if I consider this as a x-axis, so this is the x-axis and the y should be in the anti-clockwise direction. If I draw the coordinate system, so if this is x, so in anti-clockwise direction it should be y and it should be z. So that means the y is outside the board. Okay, so y, if you want to represent here, so y is outside the board. So this is the coordinate system and this is the boundary which is separating the two medium. Now if the wave is incidenting, suppose wave is incidenting from here, so this is having some propagation vector. This is the incident wave. If I am writing it as incident wave, so this incident wave is lying on which plane? You can see that I have drawn this plane wave in xz plane because it is lying in the board itself. So it means that this incident wave is lying in the xz plane, and always the incident wave always makes angle with the normal of the boundary. So normal to the boundary, because this is the z equal to 0 plane, so normal to the boundary is z axis itself. So whenever the wave will incident, it will make an angle with the normal axis, that is with the z axis here. So this is the incident wave theta I, and the some part of this wave can reflect. So this is the reflected wave. This is the reflected wave, and some part of this wave can be transmitted. So this is the transmitted wave. Now it makes angle with the normal to the boundary. So this is theta r and this is theta t. So this is the way we can represent a wave which is incidenting at oblique incidence. And with oblique incidence, as we say that the plane of incidence, what is the definition of plane of incidence? So the definition of plane of incidence is plane containing the incident wave. So this board is containing the incident wave, okay, and the unit vector normal to the boundary. So whatever boundary you consider, the normal to the boundary that board should contain. So the boundary is xy plane and normal to the boundary is z axis. So this is the normal, and this board, which is a plane, is containing the incident wave as well as the unit vector normal to the boundary. Hence we can say that this xz is the plane of incidence. Xz is plane of incidence. Xz is plane of incidence and xy is interface or boundary. Both the planes are different, and that is very important here to identify these two planes. Plane of incidence, in which the plane is incidenting and the unit vector containing the plane, or the plane containing the unit vector, is called plane of incidence. But the boundary is the plane which separates the two medium, medium 1 and medium 2. So similarly, you can draw the figure like this also. If this is the boundary, if I say this is the boundary, say x equal to 0, that means yz plane is the boundary. And since this is x axis, x equal to 0 plane, so this is suppose x axis. Now for x greater than 0, this is the x greater than 0, we are having medium 2. And this is x less than 0, we are having medium 1. So now the wave is incident from medium 1 to medium 2. So some part of this is the wave, incident wave. So some part of wave is reflected back to the same medium and some part of it may be transmitted like this. So this is the transmitted wave and this is the reflected wave, which is reflected back to the same medium. Now, how do you form an angle? So because the boundary which separates the two medium is now like this. This is the boundary, and above this boundary we have a medium 1 or medium 2. Above this we have a medium 2, and below this we have a medium 1. So this hand is the boundary which is separating these two medium 1 and 2, and it is incidenting from medium 1 to medium 2. So the normal to the boundary, normal to the hand is this x-axis itself. So if this is the boundary, the normal is x-axis. So always the plane wave makes an angle with the normal to the boundary, and the normal is x-axis. So it will make an angle with the x-axis, and when it reflects, it also makes an angle with the x-axis, and when it transmits, it also makes an angle with the x-axis. So this will be the representation of incident wave, reflected wave and transmitted wave with angle. And what would be the plane of incidence if I say? Then the boundary is that this is the boundary, this is the boundary yz, and the plane of incidence is x, and you can write it as z also. So xz will be the plane of incidence, or you can write it as y because this is the plane of incidence. So if according to the coordinates, if I say this is x, this is y, and this is z. So this time xz is the plane of incidence again, and the interface is yz. So the boundary is yz, and the plane of incidence if I write, so again here it is xz. Plane of incidence is again xz. Now the question is next definition. How do you define this parallel polarization? So let's define the parallel polarization, and to define the parallel polarization we are considering the same figure. We are considering the same figure, this figure, you can draw it again. So now we are able to define this plane of incidence, and this plane was also having the normal vector. The normal to the boundary is this one, because this time this is the normal to the boundary an. So this normal vector, unit normal vector is x, unit normal vector is ax. So this plane which we had drawn here is also having the plane of incidence which is yz, and also the unit normal vector. Unit normal vector is ax, because which is the unit vector normal to the boundary. So a plane which is containing the incident wave or propagation of incident wave or propagation of plane wave, and also the unit vector normal to the boundary. Okay. Now we want to define a parallel polarization. So parallel polarization, if the electric field of uniform plane wave is parallel to the plane of incidence, it is called parallel polarization. So this is the propagation of plane wave, and now we are saying that this incident wave will be having, because this is a uniform plane wave, so this incident wave is having electric field, magnetic field and direction of propagation. So the plane wave is always perpendicular, the plane wave has always electric field, magnetic field and direction of propagation perpendicular to each other. So if I consider the electric field, suppose in this direction, suppose wave is incidenting in this direction and it is represented by ki. This is having the propagation vector of incident wave, this is the propagation vector of reflected wave, this is the propagation vector of transmitted wave. Vector, if I am saying, so you can represent it by vector quantity. Okay. Now the concern is that if the wave is traveling in this direction, suppose the wave is traveling in this direction, because these three are perpendicular to each other. So suppose this is the plane wave traveling in this direction, and this finger is showing the direction of electric field and the thumb is showing the direction of magnetic field. So if I represent like this, it means the wave is traveling in this direction and all are perpendicular to each other. All these three are perpendicular to each other, so that means this is the direction of electric field. And if this is the direction of electric field, then it can be resolved in two components. One is this one and other is this one. One is in the direction of x and other is in the direction of z, which is negative z. Okay. So, the minus sign, it is showing that just the direction, that is going in the negative z direction. So, when you draw this electric field and when you resolve it, what you are getting is the components of this electric field is parallel to the x-axis and z-axis. So, if I resolve this electric field, it is going parallel with the x-axis, it is going parallel to the z-axis. So, both the electric field are parallel. Both the component of electric field are x and z. And what is x and z? The x and z are plane of incidence. So, what we had written here, if the electric field of uniform plane wave is parallel to the plane of incidence, so it is parallel to the plane of incidence because plane of incidence is x and z and electric field is also having component x and z. So, if these two are parallel to the x and z axis, it means that it is an example of parallel polarization. So, when you write this diagram again, you can represent it here, parallel polarization. This is the example of parallel polarization. Now, what would be the example of perpendicular polarization? Suppose this is z-axis, this is x-axis, we are going to look for perpendicular polarization. Now, suppose the wave is incidenting from here, this is the incident wave and incident propagation vector, and some part is reflected, so this is kr, and some part is transmitted, that is kt, and this is the medium 2 and this is medium 1. Always the reflected wave will be in the medium 1. So, incident and reflected wave are in the left hand side, that should be the medium 1. So, it should making with the angle theta I, theta r with the normal to the axis. So, z equal to 0 is the boundary, so which is separating the two medium. This is the boundary, left medium 1, right medium 2. So, this z axis is changing. So, this is z greater than 0 which is defining medium 2 and z less than 0 is medium 1. Now, suppose this is again the plane wave. Now, the electric field is, suppose this thumb is showing the direction of electric field. If this thumb is the direction of electric field, then what would happen? It will be represented by dot. So, this is the direction of electric field now, okay, of incident wave. This is the incident wave and the direction of electric field is represented by dot here, and this dot is actually which axis? So, if you draw the coordinates x and this is the y axis and this is the z axis. So, outside the board is representing a y axis or the y coordinate, and the electric field is in the direction of outside the board and outside the board, because now the wave is same, but now this time I am saying that my thumb is pointing the direction of electric field. This time I was saying that my forefinger is pointing the direction of electric field so that it can be resolved, and it can be resolved in the direction of x and z. That is why this is called plane of parallel polarization. And here I am saying that my thumb is pointing the direction of electric field, the direction of propagation is same, but the direction of electric field has been changed, and now the thumb is pointing the direction of electric field. And since the electric field is in the y direction and the plane of incidence is xz, it means that the electric field is perpendicular to the plane of incidence. Here we have written that if the electric field of uniform plane wave is perpendicular to the plane of incidence. So, here the plane of incidence is what? Here if I will ask you what is the plane of incidence, so the plane of incidence is nothing but xz, because it is containing the uniform plane wave and also unit normal vector to the boundary. So, this plane will be called as uniform plane of incidence. And what is the boundary? So, the boundary is z equal to 0 plane, that is xy plane. Now, the unit normal vector we have got, the incident wave we have got, the incident wave is having electric field in the y direction, and that is why this is an example of perpendicular polarization. So whenever the question is asked to you for the perpendicular polarization, the electric field of the incident wave will always be having the direction perpendicular to the plane of incidence, and the electric field is, if the parallel to the plane of incidence, it will be called as parallel polarization. So now we have got these definitions and the basic diagram or the basic idea how to represent this parallel polarization and perpendicular polarization. Now we will consider how to represent this uniform plane wave. Okay, how to represent this uniform plane wave. So for that there will be some standard form of the equation, like we consider in the starting of this chapter. If we want to represent a wave, then that is always given as E naught e to the power minus alpha z cos of omega t minus beta z, and a E, whatever will be the direction, AE or AH, whatever you want to write. So if you want to write electric field, you write it as AE, and if you want to write magnetic field, you write the direction of magnetic field AH, but all are having the same representation. So in that way it is also having some component, but as we saw that this electric field can be resolved here. So if we resolve electric field, then it may have x component, it may have y component, it may have z component. So it can have any of the direction. So let's represent how to represent the plane wave with oblique incidence. So representation of wave with oblique incidence. Okay. So this would be, suppose the electric field with suppressing the time factor. Okay, let's consider the time factor as well. Then if we resolve, it may have x component. So let's consider the coefficient of x and in the direction of x. Electric field may have the y component, as we did resolved in the case of parallel polarization, it has x and z component. So it may also possible that it has a y component and it may have a z component. So actually any plane wave is the combination of parallel and perpendicular polarization, we can write. This is a combination of parallel perpendicular polarization, because the example which we consider, first example was parallel polarization in which x and z was there. So x and z was there, and in the second example it was a y component is there. So these two is forming a parallel polarization and the y component is forming a perpendicular polarization as the diagram which we consider. It is not always possible, but it depends on the plane, but we can say from the previous two diagram that x and z are parallel polarized and the y is perpendicular polarized. Now e to the power j omega t minus k dot r. This is the representation of plane wave. Whenever you want to write the expression of plane wave with normal incidence, with oblique incidence, you have to write equation in that way. This is important. Okay, so here K is called propagation vector. This propagation vector is defined as kx ax cap plus ky ay cap plus kz az cap. This is the propagation vector kx ax, because as you have seen in the previous diagram, if the wave is incidenting with making some angle like this ki, and if it is x and this is z, then this ki can also be resolved. And if I resolve this propagation vector ki, then it may have the x component and z component and y component. So similarly, this is also having a x component, y component and z component. So we are defining it in general because we don't know about the plane. It may have any two component, it may have only three component, it may have only one component. We don't know about this, but we know that the plane wave is incidenting on a plane, so it will at least have two components. So it is having at least two components. So which two components it will have, we don't know. So that's why we are writing in general, it may have all components. Now the beta, that is known as phase constant of the medium, phase constant, is defined as the magnitude of propagation vector, magnitude of propagation vector, which is equal to root over kx square plus ky square plus kz square. And this phase constant or k is also known as wave number sometimes. So wave number, if it is written in the form of wave number, then don't confuse with this. This is nothing but beta or k. Now what is r here? So the r is known as position vector. And this position vector can be x ax cap plus y ay cap plus z az cap. This is the position vector. This is always fixed. We will not change in any part of the calculation value of r. The value of r will be same throughout every consideration. So we have to take the k dot r. So whatever we will get, we will write according to the value of k. Because as you calculate the value of k dot r here, suppose what you will get, ax dot ax will be 1, so we get kx into x, ky into y, kz into z. This will be the k dot r. So as you can see that if this z is some constant, so it means that you get some equation of plane like 2x plus 3y plus 4z and so on. So this is the k dot r. Let's consider one example I consider for you, that how to draw a figure if the equation is given to you. Okay. So for example, suppose the electric field is given in this form, E naught x ax plus E naught y ay and e to the power j omega t minus 3x plus y. So from here we can write the value of k dot r. So the value of k dot r is 3x. If I take the minus sign common, because in the standard form, see here, the standard form minus sign should be there. So I have to take the minus sign common, and if I represent in this form e to the power j omega t minus sign is common, so it should be 3x minus y. This would be the representation. So k dot r is 3x minus y. Now the value of r is fixed. The value of r is fixed, that x ax plus y ay plus z az. Then what should be the value of k? So the value of k should be, to get this, what should be the value of k? So it should be 3ax minus ay cap. If this is the value of k, then we, after this dot product k dot r, we will get this equation, because this ax dot ax is 3x and ay dot ay is minus y and az is 0. So in this way you have to write the propagation vector. So once you get the propagation vector, now you can calculate the value of beta, which is the root over kx square ky square plus kz square, that is the magnitude of vector k. So this is the, if you calculate the magnitude of this vector beta, you will get 3 square plus 1 square, which is root 10. So this is the value of beta for this example, you can consider. Okay, so if this is 3x and y, then just you have to write the unit vector, whatever variable associated with the k dot r, you have to write only the unit vector in case of k. So this coefficient is 3, so 3ax cap, and the coefficient is minus 1, so minus ay cap, so 3ax minus ay. because I am not going to change the value of r. So you have to consider the k in such a way that after dot product you should get the same value. So for that you have to consider the coefficient of k dot r in propagation vector. So only consider the coefficient, and the variable associated with this is the unit vector. The x is associated with this, so we will multiply with the unit vector ax with 3. The associated variable is y, so that's why unit vector will be ay with coefficient -1. So that would be the value of beta. Now let's draw it. If it is x and if it is y. So the wave should incident in such a way, this is the equation of incident wave. So the wave should incident in such a way that when the propagation vector is resolved, the x component should be positive. From here you can see this is the direction of propagation vector. So the x component is positive and y should be negative. So the x component should be positive and y should be negative. That means the wave should incident from here. If the wave is incident from here, suppose this is the propagation vector of incident wave. So the wave is incidenting from here now, and it is suppose reflected back to this and transmitted some part in the next region. Let us say like this. So this is the reflected wave, this is the transmitted wave I am saying, but the important thing is how you have to incident the wave. So here the wave is incident with propagation vector ki, and when I resolve this, I should get the x component positive and y component negative. So x component positive, that is in the positive direction because this is x-axis, so it is in the positive direction, and it is in the minus y direction because this is 0, so this is the negative y. So this is the propagation vector which we can represent according to the equation. The diagram is like this. Okay, so here suppose the boundary is y equal to 0. So y greater than 0 is medium 1 and y less than 0 is medium 2. Y greater than 0, medium 1, medium 2, y less than 0. We are assuming like this. So y equal to 0 is the boundary. So the incident wave will make an angle with the y axis. So it will make an angle with y axis. So this is theta I, theta r, theta t. This would be the representation. You can draw the same figure in a different way. Suppose this is the y and this is x. I just assume that y equal to 0 is the boundary. It may be anything, but the important thing is that you have to consider the plane xy and in such a way that x should be positive and y should be negative. So if suppose I want to consider the wave to be incident from here, so I want to have the x positive and y negative. That means the x positive in downward direction and y negative, that means in this direction. So this should be the minus y axis. So accordingly we can change the coordinates also. So this should be the plus x axis and this should be the minus y axis. So this would be the incident wave and it makes an angle suppose with the y axis because we consider the y equal to 0 is the boundary. So with the y axis it will make an angle. So here it is reflected back kr and now it is transmitted to next region kt. So here also you can see that y less than 0 is 2 and here also this is the y less than 0 part, y less than 0 and it is, let us define as medium 2 and this is y greater than 0 and it is medium 1. So the wave is incident from here and it is reflected back to the same medium, so that is the medium 1 and it is transmitted to the next medium, that is medium 2 and it is making an angle with the y axis, so this is theta r and theta t. So when you resolve this incident wave, it is important that the equation given to you in the question, that should be satisfied. So if the wave is incident from here, so when you resolve it, you have to get the x component positive and y component negative, and for that you can reverse the coordinates or you can reverse the axis. So that's why when I am resolving this, I am getting this as negative direction. So negative direction, but it should be having a positive value of x. So that's why I kept the positive x-axis downward and the negative x-axis upward. So I inverted the axis. So this is the positive x-axis, this is the negative x-axis, but in this diagram I have inverted it, and the y component we should get is in the negative y direction. So this is minus kiy. So this is in the negative y direction, this is our negative y axis and this is our positive y axis. So in this way we can draw the figure according to our convenience, but the thing is we should follow the equation which is given to us. So this is the representation of wave. Here we are not considering the parallel polarization and perpendicular polarization. Here we are considering that how to decide plane of incidence and how to draw the figure with the equation given to us in case of oblique incidence. So whenever the equation is given, according to that equation we can draw the figure, and important thing is in the question the boundary is also given. Here we assume by our own convenience the boundary is y equal to 0, but if the boundary is x equal to 0, then the figure will be different. That will be the different case, and if the boundary is x equal to 0, then there should be x-axis that is varying this separating these two medium, and you can consider that also. Let's draw the figure for this. If it is x-axis, okay, if the boundary is x-axis. Now suppose the boundary is x-axis like this. This is the x-axis and I am saying that x equal to 0 is the boundary. So this time this is the plane which is separating the two medium. So when it is incident from here, it will be reflected back to the same medium. We are saying that x less than 0 is the medium 1 and x greater than 0 is the medium 2. Now if wave is incident from here, we should have a incident propagation vector in such a way that it should have the x component positive and y component negative. So when I resolve it, this is the x component in the positive direction, so this will be kix, but when I resolve it, it should go into the negative y direction. So this axis should be a negative y axis and this axis should be plus y axis. Then only this equation will be satisfied with x equal to 0 boundary. So if wave is incident, here it is reflected in the medium 1 itself and it is transmitted in the medium 2. So this is the boundary is x axis, so it will make an angle with the x axis. So this is theta I, theta R and theta T. Because the boundary is x equal to 0, it will make an angle with the x axis. So that's why theta I, theta R and theta T we have represented, and since the x equal to 0 is the boundary, this is the boundary which is separating the two medium. This is medium 1, this is medium 2, and the wave when incidenting, it should satisfy the given equation. The given equation should have the x positive and y negative. So when I resolve it, the x component should go into the positive direction. For that I have to take this as x-axis and this should be the minus y-axis because wave is incidenting from here. If you want to make it incident from here, then you can change the coordinates. So this is the representation of a wave in case of oblique incidence. Now we will derive some Snell's law. We will apply the Snell's law and how do we get the angles in case of incident angle is given and the transmitted angle we can calculate, and some boundary condition which should be satisfied that will be considered. So next is condition that must be satisfied for all value of x and y. So let's write conditions that must be satisfied for all x and y. Omega I, first condition is omega I, omega r and omega t should be equal to omega. That is known as frequency matching condition. This is known as frequency matching condition. And the second one is KIX, KRX and KTX, that is the transmitted propagation vector, reflected propagation vector and the incident propagation vector in x direction is equal to Kx, and KIY is equal to KRY is equal to KTY is equal to KY. This is called phase matching condition. This should be satisfied. Let's consider this. Now suppose we are having a plane of incidence, that is a XZ plane. So here we are assuming that XZ plane is the plane of incidence and Z equal to 0 plane is the boundary. Generally you will find this type of assumption only in the case of plane of incidence. So this is Z equal to 0, this is Z greater than 0, we are having medium 2. So this medium 2 is lossless medium because we are assuming only the lossless medium. So it is alpha 2 equal to 0, and this is medium 1 in which also alpha 1 is 0 because this is a lossless medium. Now the wave is incidenting. So let's say wave is incidenting with the normal to the boundary is the z axis. So it will make an angle with the z axis. So this is theta I, this is theta r, this is kr, this is theta r, and this is kt. Propagation vector, transmitted propagation vector, incident propagation vector, it will make an angle with the z axis. So this will be the representation. Now we have to apply this boundary condition. So let's consider this boundary condition, Kix equal to Krx. So when we resolve this, what are the different components we will get? So this is the Ki in the direction of z, this is Ki in the direction of x. If this is the reflected wave, so if we resolve this, we will get Krz in the negative direction, and this is Kix, Krx in the reflected wave in the x direction. And here also we are having Ktz and Ktx. Now we want to apply this boundary condition that Kix equal to Krx. So Kix equal to Krx means Kix into Krx. So incident wave x component should be equal to the reflected wave x component. So incident wave x component is, if we resolve this, we will get Ki vector magnitude, and if this angle is theta I, so this angle will be theta I. So this is Kix is the sine component. So Ki magnitude and sine of theta I, it is equal to Kr magnitude and sine. Again you can see that this is theta r, so this is theta r, so this is also a sine component. So Krx is also a Kr vector magnitude and sine theta r. So the magnitude of propagation vector of incident wave will give you the phase constant of incident wave, and the magnitude of propagation vector of reflected wave will give you the phase constant of the reflected wave, and both the wave, incident and reflected wave, are lying in the medium 1. It means that the propagation vector having a magnitude is giving you a phase constant which is only for the medium 1, because the phase constant is defined with the help of characteristics parameter of medium, and since the characteristics parameter does not change of medium 1, that's why whether you calculate the magnitude of Ki or you calculate the magnitude of Kr, both will give you the same phase constant, that is it will be beta 1 sin theta I is equal to beta 1 sin theta r. So this equation will give you the angle of incidence is equal to angle of reflection, which is known as law of refraction. So this is the theta is equal to theta r, which we also studies in ray optics, that the wave which is incidenting with the angle of incidence theta I reflects with the same angle theta r. So theta I is equal to theta r. Now let's consider this first and third, because this should also be equal. So this is Kix equal to Ktx, Kix equal to Ktx. So Kix equal to Ktx means this is the incident propagation vector Ki, and x component is sin theta I, and Ktx. So now Ktx, you can see that this is theta t, this is also a theta t. So in the normal direction, this is a sine component. So this is Kt vector, its magnitude, and sine component sin theta t. So Ki magnitude is beta 1 sin theta I, because this will give you the phase constant of medium 1. So Ki magnitude will give you the phase constant of medium 1, and Kt magnitude, and because the Kt, which is the propagation vector in the second medium, so the constant, the phase constant will be for the second medium. So it would be beta 2 sin theta t. So this is the important relation which we are going to use for the calculation of transmitted angle. So this is the important equation. So beta 1 sin theta is equal to beta 2 sin theta t, and by using this equation we most of the case we calculate the angle of transmission and angle of incidence if any one is given. Now we can even expand this, because if suppose beta is equal to, for lossless, omega root mu epsilon, so mu 1 epsilon 1, this is sin theta I, and omega root over mu 2 epsilon 2, because both the medium are lossless, so we can represent it like this, sin theta t. This omega and omega will get cancelled. If I multiply both the sides by velocity of light, that is c root over mu 1 epsilon 1 sin theta I is equal to c root over mu 2 epsilon 2 sin theta t. Now this c into root over mu epsilon, what it represents? So if I represent the definition of refractive index, see here, a refractive index n equal to, this is the velocity of wave in vacuum divided by velocity of wave in medium. This is the definition, and velocity of wave in vacuum is nothing but the velocity of light, so it is c, and we calculate the velocity of wave in any lossless medium by phase velocity Vp, which is also equal to root over mu epsilon, 1 upon root over mu epsilon. So 1 upon root over mu epsilon, so it will go into the numerator c into root over mu epsilon. So c into root over mu epsilon is actually the refractive index of medium 1. So it is the refractive index of medium 1, which is represented by n sin theta I is equal to n2 sin theta t. This is the refractive index of second medium. So n1 sin theta I is equal to n2 sin theta t. So this is nothing but the Snell's law. This is Snell's law. So from here we can calculate or relate the angle of incidence equal to angle of reflection, and the eta 1 sin theta I is equal, n1 sin theta I is equal to n2 sin theta t, or we can calculate beta 1 sin theta I is equal to beta 2 sin theta t. So this is the most important equation which we will be using in case of parallel polarization, perpendicular polarization. And this is the Snell's law, which we also study in our intermediate school classes 11th and 12th. You can also study in that. In the physics also we studied that. So this is the in general form, the boundary condition that we apply, that is the condition that must be satisfied, which is the frequency and phase matching condition in this case. Now we will consider how to write the equation of electric field, incident electric field, reflected electric field, magnetic field, incident electric magnetic field, reflected magnetic field, transmitted electric field, transmitted magnetic field, as we did in case of normal incidence. And from there we define the equation of the reflection coefficient. We also define the transmission coefficient, and now here we will define the Brewster angle. What is the Brewster angle? At which angle of incidence we consider the angle is Brewster angle. So that all we will define, and next topic will be parallel polarization. One more thing that you have to consider in this part is that how do you calculate the angle of incidence from this diagram. So if once you have made this diagram, how to calculate angle of incidence if the equation is given to you. You can see that this is the value of theta I. Suppose if I perpendicular line up to this axis, so this is the tan theta I and this is kix. So up to this distance, this is kix. So this is the kix and this is kiz. So the angle of incidence you can calculate as tan theta I is equal to kix divided by kiz. It is not always the case, but when you draw the figure you can calculate. It is not like that angle of incidence is always equal to x component divided by z component. It is not always the case. But whenever the you can write the propagation vector from the equation given to you. Suppose the electric field equation is given to you, and from there if you write the angle, the propagation vector of incident wave. So after that you will draw the figure, and after drawing the figure, when you draw the perpendicular line to both the axes, you will get the ratio as tan theta I, and this tan theta I you can see that this is the ratio of x component and z component. So whatever propagation constant you will get, the coefficient of x and the coefficient of z, take the ratio of these two, you will get the theta I if the figure is like this, and if the figure is different, then the angle of incidence will also be different. So when we will solve the numericals, we will see the diagram. Let us say, I will do it for you. Suppose the electric field is given in this form, whatever it is. Important thing is we are considering that 3x plus 4y, okay, in this way. So the x component and y component both should be positive. So you will make the diagram in such a way that when you resolve the propagation vector, you will get the x and y component positive. So if this is x and this is y, suppose, then if the wave is incident from here, then you will see both the component. This is the propagation vector, and both the component in positive direction. This is kix and this is kiy. And if this is theta I, suppose, if this is theta I, means the normal is y-axis. Okay, so how do you calculate this angle of incidence? So you will draw the perpendicular line in both the axes, and this is theta I. So this value divided by this value. This value is kiy, so this value is also kiy, and this is kix. So now if I apply tan theta I, it would be kix divided by kiy. So now it is different from the previous that I wrote, because it depends on the plane. If the plane is xy, it is like this, and it depends on the whether it is making an angle with the y-axis or x-axis. It also vary. So the x component is having coefficient, the x component is having coefficient 3, so it is 3, and the y component is having coefficient 4, so it is 4. So now you can calculate the value of theta I. And how it is the coefficient of x and y? So I told you the variable associated with this, you have to take the unit vector. So if I write the ki vector, incident propagation vector, that would be 3ax plus 4ay. So you have to associate the unit vector with the which variable is associated with this. So the variable associated with this is x, so associate 3 with the unit vector ax. 3 with unit vector Ax, and the unit vector, here the variable is 4, y, the variable is y, so associate the unit vector Ay with 4 into Ay. So this is the propagation vector, this is the angle of incidence. In this way we can consider the angle of incidence, and once the angle of incidence is known, we can calculate the transmitted angle using this equation, because this beta 1 and beta 2 will be known to us, because the medium characteristics should always be given in the question. So this beta 1 and beta 2 we can consider, theta I we can calculate from the equation or the diagram directly, and then we can calculate theta t. And this type of question has been asked in GATE. So this is important concept, that how to calculate angle of incidence from a given equation. Next topic is parallel polarization. So in case of parallel polarization, we know that the electric field should be parallel to the plane of incidence. So we have to consider the figure in such a way that electric field should be parallel to the plane of incidence. So I am considering the plane of incidence as same xz that we consider in the previous discussion also. Okay. So this is medium 1 and the wave is incident in this region, and the boundary is z equal to 0. So z equal to 0 is the boundary. So this is the medium 2 and this is the medium 1. So let's write it here. This is medium 2, z greater than 0, and this is medium 1, z less than 0. Now the wave is incident from here like this. This is the incident propagation vector Ki. So the wave is incident from here, and we have considered the boundary z equal to 0. So remember that we have considered the boundary z equal to 0 is the boundary, and xz is the plane of incidence. Okay. Now the wave is incident, so that is the incident propagation vector. Now because z equal to 0 is the boundary, it will make the angle with the z axis. So it will make the angle with the z axis at theta I, and as we have derived that the theta I equal to theta r, so this should go with making the same angle with the z axis theta r, and this is kt, that is the kr, that is the reflected propagation vector. Kr, this is the reflected propagation vector. So the wave is incident from here, it will go into the same medium because this is a reflected wave, and some part of it may be transmitted. So this is kt, that is the transmitted propagation vector. And it will also make an angle with the z axis theta t. So this is the diagram according to the propagation vector, but we are talking about the specifically in case of parallel polarization. So when we talk about the parallel polarization, we have to make in the electric field in such a way that it should be parallel to the plane of incidence. So the plane of incidence is xz, so it should be parallel to the x and z. So let's draw the electric field here is this. This is electric field, incident electric field, EI, incident electric field. So now when you resolve this, you can see that when you resolve this, you can see that it is making when it is resolving, when resolved, the one component will be in this direction, other component will be in this direction. So it is one component which will go in this direction is parallel to the x-axis, another component which will go into this direction will be parallel to the z-axis, that is the parallel polarization. So this is theta I, so this will be theta I, and if this is theta I, this will be the 90 minus theta I, because this is a vertical line and there is horizontal line, so this will be the 90 minus theta I, and the direction of propagation in electric field should have the 90 degree, so it means that this angle will be theta I. I hope it is clear to you. This is these two are perpendicular to each other actually, like this. They are perpendicular to each other. This is the direction of electric field, this is the direction of propagation, they are perpendicular to each other. Now, we have to make magnetic field also. What would be the magnetic field at this point? So, if this is the direction of electric field, this is the direction of magnetic field, then according to the right hand rule or the relation of this propagation vector, AH is equal to AK cross AE. So when you curl the finger from direction of propagation to electric field, the thumb will be pointing will be the direction of magnetic field. So this is the direction of propagation and this is the electric field. So when I curl my finger from the direction of propagation to electric field, the thumb is pointing in outside the board. That means this would be the direction of magnetic field. So HI outside the board will be the direction of magnetic field. According to the right hand rule, this is the direction of propagation, and when I curl finger from the direction of propagation to electric field, why? Because AK cross AE should be satisfied. AK cross AE, that means direction of propagation to electric field, you have to curl your finger. So this curl of finger from the direction of propagation to electric field is actually thumb is pointing in outside the board. That's why the magnetic field will be in outside the board. Now, this is suppose KR. Now let's consider the direction of electric field somewhere in this direction. This is an assumption, so it is not like that always electric field should point in this direction. It is not like this. Whatever given to you in the figure, you have to consider. So I am considering the electric field in this direction. So direction of propagation and direction of electric field, you can see that this, if I extend it, so this will be the direction. So this is the direction of KR. So direction of propagation to electric field, direction of propagation to electric field, if I curl my finger, direction of propagation to electric field, the thumb is pointing inside the board. That means here the magnetic field is represented by a cross, that is inside the board, that is HR. So what would be the angle? So if it is theta R, then this will be theta R. Then the electric field and the direction of propagation is 90 degree to each other. It is 90 degree to each other. So this will be 90 minus theta R. So this will be theta R. So this is the representation of electric field. Now you have to represent here also. So the incident wave and the transmitted wave will always having the same direction as we discussed in the normal incidence. The incident wave is making whatever the direction it is having the electric field and the magnetic field, the same direction it will be having in the transmitted wave also. So if electric field is represented here in this direction for the incident wave, so the transmitted wave will also be having the same direction, and if the magnetic field is having the dot that is outside the board, then the transmitted wave will also be having the magnetic field outside the board. So that is HT. Now if I consider the angle here, then So this is theta t, so this should be theta t and this should be theta t. This is the alternate angle. The direction of electric field and direction of propagation is 90 degree to each other. So this angle is 90 minus theta t, and this is horizontal, vertical line and horizontal line. So the total angle should be theta t. So if you add this, you will get theta t only. So this is how we define the, or how we denote the angle in this diagram. So we have made all the we have made the diagram in all, considering all the facts that is considered in case of parallel polarization. So here we are assuming that Ki is incident propagation vector, and incident propagation vector is in the medium 1. So the beta 1 is nothing but the magnitude of incident propagation vector, and Kt is transmitted propagation vector. So beta 2 would be the magnitude of vector Kt. This is about the second medium, so that's why the magnitude of the Kt will give you the beta 2, which is the phase constant of second medium. Okay. Now finally we have made all the diagram and all the respective terms. Now we have to write the equation. So how do we write the equation? So electric field is represented by some value, peak value, whatever it is, its direction, including its direction, whatever it may be. The direction I am not writing, but the important thing is e to the power j omega t minus k dot r. So depending on which wave you are writing the propagation vector, you have to consider. If you are writing a incident wave equation, then you have to consider the incident propagation vector, and if you are writing the equation of electric field and magnetic field for the reflected wave, so if you are writing for the reflected wave, then you have to consider the reflected propagation vector. If you are writing for the transmitted wave, you have to consider the transmitted propagation vector. So if I suppress the time factor as well, then suppressing the time factor E naught A E cap and e to the power j omega t will be there. E to the power, we are suppressing the time factor, so we don't have to consider the time factor. So if I ignore this time factor, then I will get minus j k dot r. So this way, in this way we will write the equation of electric field. E naught, that is the peak value of electric field and its direction, and e to the power minus j k dot r. So let's try to write for the incident wave first, then you will come to know how to write for the reflected wave and transmitted wave. So as we did in the normal incidence, we wrote the 6 equations, and on the basis of this 6 equation we found the equation of reflection coefficient. In a similar way we have to find here also. Now this is the electric field, and this is the propagation vector. This electric field is having two components. One is cos component, and the cos component is going in the upward direction. You can see this is in the upward direction, and the sine wave is in this direction, which is left hand side. So the field component which is going upward direction is the x-axis, which is the positive x-axis. So that means the electric field is having a cos component in the positive x direction. This electric field is having sine component in the negative z direction, because the plus z axis is this one and it is moving towards left, that is it is moving in the negative z direction. So let's consider EI, suppressing the time factor. The peak value is EI naught because of incident wave. This EI naught and the cos component, cos theta I, it is in the plus x direction, so this is plus AX in AX. So this EI is having a peak value EI naught, because when we resolve we take the magnitude of it. So the EI is having the magnitude, let us say EI naught, and the cos component is in the positive x direction, so this is in positive x direction, and the sine component is the negative z direction. So this is plus EI naught sine component sine theta I, but it is in the negative z direction, so unit vector will give you the direction. So this is the electric field only. Now this part I had written E naught AE, that means the peak value and its direction, and the peak value which we have to consider according to the components, and the components are cos and sine that we have to consider. Now I have to write e to the power j k dot r. So what is the value of k here? For incident wave, before writing here, I am calculating here this ki. What should be the value of ki? Incident propagation vector. If you will see from the diagram, this is the incident propagation vector. It is also having the two component. One is this cos component. In this direction we are having the cos component, and in this direction we are having the sine component. The cos component is going in the z direction and the sine component is going in the x direction, because both are upward direction, ki x and ki z. So both are in the positive direction. So it means that ki vector magnitude cos component cos theta I, which direction? In the z direction, that is az cap. Then ki vector magnitude sine component, which direction? X direction. So magnitude of ki is represented as beta 1. So we can write this as beta 1 cos theta I plus az cap plus beta 1 sine theta I ax cap. This is the ki propagation vector. Now we have to take the k dot r, and I told you that I will not change r, that is the position vector. So the r will be always x ax plus y ay plus z az. So if I take the dot product of these two, ki dot r, it would be the dot product x dot x is 1. So hence we get beta 1 sine theta I into x plus z with z, that means beta 1 cos theta I into z, and the y component is not there, that means the dot product will be 0. So this would be the ki dot r. So now we will write the e to the power here, e to the power minus j k dot r. So the k dot r we have calculated, that is x beta 1 sine theta I plus z beta 1 cos theta I. So this is the first equation that we want to write for the incident wave. Now when the wave is incidenting, so there will be no change in propagation vector, because incident wave is in this direction, that means it will be same for electric field and magnetic field, because all are having the same wave, just we are writing the electric field and the magnetic field. So the propagation part will not change, this propagation vector will not change. So how to write this equation of magnetic field? So let's write HIS. So it should also have some peak value. So let us say this peak value is H naught. And what is the direction of electric field? What is the direction of magnetic field? It is having a peak value, let us say HI naught, because we are talking about the incident wave. This is our incident wave, so we are talking about the incident wave. So what is the peak value of incident magnetic field? So let us say the peak value of incident magnetic field is HI naught. And the direction of H is outside the board, and outside the board is which axis? If this is x, this is z, then according to the coordinate system, this is x, if this is z, so in anti-clockwise direction that should be y, because x, y, z in anti-clockwise direction it should have. So x to y, y to z, that means outside the board it is a y axis. So the magnetic field is having a y component, that is positive y, ay, and propagation vector will not change, as I told you that the wave is travelling still in the same direction, and if it is travelling in the same direction, then ki and r will not change for this wave, and if it is not changing, that means the propagation vector here you will get k dot r will be same, that means x beta 1 sin theta I plus z beta 1 cos theta I. This is equation number 2. Not equation number 2 right now, don't write equation number 2. Now, once we write the magnetic field, we denote in terms of eta also, as we did in the normal incidence. And what is the relation? So, because this incident wave is in medium 1, the intrinsic impedance of medium 1 is given as EI naught divided by HI naught. The peak value of electric field divided by peak value of magnetic field is given as intrinsic impedance of that region. So, HI naught can also be written as EI naught divided by eta 1 AY cap e to the power minus j x beta 1 sin theta I plus z beta 1 cos theta I. This is equation number 2. So, we have got the 2 equation for incident wave. Similarly, we will get the 2 equation for the reflected wave, we will get the 2 equation for the transmitted wave, and hence we get the 6th equation, and out of that 6th equation we have to find the equation of reflection coefficient. So, as you can see that if the wave is reflected or the transmitted, if the wave is incident in the medium 1, then the coefficient is beta 1, and you can see that it is having a z and x component, then the variable x and z is multiplied. So, sin theta is having a x component ax, then the variable x is multiplied in the propagation vector k dot r, and the cos component is having a unit vector az, so it is multiplied with the z. So, cos component with z. So, it means that whatever will be the direction, the component we have to multiply with the variable in which the direction is there of reflected wave. So, let us write for the reflected wave. ERS. So, reflected wave should have some peak value, that is, let us say ER naught. Now, let us see from this diagram what are the different components this reflected electric field is having. So, this is the cos component, and this cos component is going in the x direction, and that is in the positive x direction, okay, and this is the sin component which is going in the positive z direction. So, we are having 2 components of reflected electric field, both are in positive. One is in the positive x direction, other is in the positive z direction. So, this is z and this is x. So, cos component is in the plus x direction. So, let us write ER naught cos theta r in plus x direction, that is ax cap, and ER naught sin component in plus z direction, that is az cap. So, this is the direction of electric field with its peak value. Now, e to the power minus j, now we have to consider this k dot r, and because we are writing it for the reflected wave, so here the propagation vector should be kr, and kr dot r we have to do, and the difference between these two is if I take the dot product with r, we have to just multiply with the variable in which the direction is of the reflected wave is given. So, this reflected wave is having a cos wave in the negative z direction, that means we have to multiply with the z only, and when we take the dot product we will get the z, and this is the sin component. As let us write here, I am writing it for you here, I am changing it here. So, we will get this kr, the cos component in the negative z direction, okay. You can see that this is the cos component, this is the cos component, and in which direction it is going? Minus z direction, minus z direction, and the sin component is still in plus x direction. So, the magnitude of kr does not change. So, this is beta 1 cos theta I only, but the angle we should write theta r, okay. The angle we should write is theta r, because we are now talking about the reflected wave. So, the wave which is making an angle is theta r. Reflected wave is making angle theta r. So this minus sign will be here. So this is minus beta 1 cos theta r is z, and it is also beta 1 sin theta r is z. So as you can see that there is no change in magnitude, because beta 1 cos theta I is also there, and here it is beta 1 cos theta r, and we know that theta I and theta r are same. That means the magnitude is not changing, but the direction is changed. Now the direction of z is negative. Previously for the incident wave the direction of z was positive, but this time the direction of z is negative. So that is the only change. So while you writing the equation in the exam, you for the reflected wave you just have to consider the direction, the magnitude is same. If suppose k dot r you are getting 3x plus y for a incident wave, then it may be 3x plus y for the reflected wave, just the direction is inverted. I have taken the direction of x as negative, as here we are getting the direction of z as negative. Similarly, suppose I get the direction of x negative, then I will write minus 3x plus y for the reflected wave. Okay, so this may be the consideration. You don't need to calculate the k dot r again for the reflected wave, because the reflected wave is having the same medium, so the magnitude will be same for kr and ki, and the magnitude is nothing but beta, that is the phase constant of that medium. Now this kr dot r. So now you take the dot product, then the x will be same, the angle is changed. Now here it would be minus sign and the angle is changed. Because the z component is having the negative sign, so that component is having the negative sign, so we will get this one. Okay. Now this is the k dot r. Now we can write directly in this equation. So we are having x beta 1 sin theta r minus z beta 1 cos theta r. This is equation number 3. Now HRS is HR naught. The direction is minus AY, you can see from the diagram, and the propagation vector does not change. So x beta 1 sin theta r minus z beta 1 cos theta r. And this HR naught can be written as ER naught divided by eta 1, because the medium is medium 1 only, and minus AY cap and e to the power minus j x beta 1 sin theta r minus z beta 1 cos theta r. This is equation number 4. Now the transmitted wave. Now the transmitted wave, we have to write the equation for the transmitted wave, that is ETS suppose. So ETS, it is having the peak value ET naught. Okay. So this transmitted electric field is having the cos component in the positive x direction and sine component in the negative z direction, because it is opposite direction. So the cos component is in the positive direction. So ET naught cos theta t positive x direction and ET naught sin theta t in negative z direction. This is the electric field, and now we have to write e to the power minus j kt dot r. Now we want to write this kt dot r. Again we have to just see the kt, and the dot product with r is just the variable that we have to associate according to the direction. So the magnitude of kt will be beta 2, because it is medium 2. So the magnitude of kt is beta 2. So beta 2 cos component is in the positive z direction and sine component is in the positive x direction. So both the components are positive and cos component is in the positive z direction. So we will multiply with the z and cos theta t beta 1. Z beta 1 cos theta t and x beta 1 sin theta t. This is equation number 4. Okay. Now HTS is ET naught. We know that we have to consider in this way. So electric field is peak value and divided by eta 2, because we are talking about the medium 2. So divide by eta 2, and it is having the plus y component as in case of incident wave. Incident wave is having the y component, so the transmitted wave will also be having the same component. Now e to the power minus j in bracket, this is z beta 1 cos theta t plus x beta 1 sin theta t. This is equation number 6. So we have got all the 6 equations. This is equation number 5 and this is equation number 6. So we have got all the 6 equations, and according to this 6 equation we have to write the boundary condition. So which is the tangential component and which is the normal component, that is important. So how do we write this boundary condition? So we know that the boundary condition is the tangential component in medium 1. Let's write boundary condition first. Boundary condition of electric field and magnetic field. Tangential component of electric field in medium 1 is equal to the tangential component of electric field in medium 2 at boundary, that is boundary is z equal to 0, and also the tangential component of magnetic field in medium 1 is also equal to tangential component of magnetic field in medium 2 at z equal to 0. So this is the boundary condition. This is the boundary condition, that the tangential component in both the medium should be same of electric field and magnetic field. So what is the tangential component? So the electric field which is in the direction of what should I say, that electric field having the component parallel to the boundary is called tangential component, and the electric field which is normal to the boundary is normal component. What is the boundary? Boundary is z equal to 0. So what will be the normal to the boundary is z axis. So the electric field which is having the z component is known as the normal component of electric field, and the remaining would be the tangential component. So here we can see that this electric field is having the x component as well as z component. So this z component is the normal component of electric field and this is the tangential component of electric field. Similarly, for the magnetic field, the electric field which is in the direction, the magnetic field which is in the direction of z will be the normal, and the remaining, that is x and y, will be the tangential. So the magnetic field is having only the y component, so it is tangential. This is the tangential component to the boundary. Similarly, this reflected electric field is having a x component and z component. Z component will be the normal because the z component is the normal to the boundary, and this is tangential. Here it is tangential. Here it is tangential, and this would be the normal, and this is y component, so this is tangential. Now we have to make the tangential component of medium 1 equal to the tangential component of medium 2. So medium 1 is having a two wave, that is incident wave and the reflected wave. So the tangential component of incident wave plus tangential component of reflected wave will be the total tangential component in medium 1. So the tangential component of this in incident wave, that is the x component only, plus tangential component of reflected wave, that is this x component only, and that should be equal to the tangential component, that is this one, at z equal to 0. So now we will consider the z equal to 0 total electric field in medium 1 and medium 2. So let's write, I am not cleaning this part so that because we need to write it we have to use it again here. So let's write here. As you can see, at z equal to 0, when I substitute z equal to 0, this term will be 0 and the tangential component. So let's write at z equal to 0, tangential component will be tangential component of region 1 is equal to sum of EIS at z equal to 0 plus ERS at z equal to 0. This is the total tangential component of medium 1. Okay, this is the total tangential component of medium 1. This part I am writing. Now at z equal to 0, incident wave tangential component is this x component only. So this would be EI0 cos theta r theta I. No need to write x component, AX, because we are writing tangential component, that is x component itself, and e to the power minus j x beta 1 sin theta I, x beta 1 sin theta I, because when you put z equal to 0 here, it will be 0, so this term will be left and this we have written here, plus at z equal to 0 ERS. So at z equal to 0 from ERS, so this is the tangential component, and at z equal to 0, this term will be 0. So this is ER naught cos theta r. So plus ER naught cos theta r e to the power minus j x beta 1 sin theta r. This is the tangential component of region 1. Now you have to write the tangential component of region 2. So at z equal to 0, tangential component of medium 2 is only ETS z equal to 0. Because in the medium 2 there is only one wave, and in this wave what is the tangential component of electric field? So that can be found from the equation number 5. So this is ET0 cos theta t e to the power minus j x beta 2 sin theta t. You can write from here, this is the x component which is the tangential component, ET0 cos theta t, and z equal to 0 means this term is 0, e to the power minus j x beta 1 sin theta, beta 2 should be there, okay, this beta 2 should be there, right, because this is the transmitted wave now, so it should be beta 2 not beta 1, okay, so this should be beta 2. So we get x beta 2 sin theta t, here I have written is x beta 2 sin theta t. So this should be equal. So according to this boundary condition, these two equations should be equal. So that is EI0 cos theta I e to the power minus j x beta 1 sin theta I plus ER0 cos theta r e to the power minus j x beta 1 sin theta r, it should be equal to ET0 cos theta t e to the power minus j x beta 2 sin theta t. This will be the equation. Now we know that this theta I equal to theta r, and we also know that this beta 1 sin theta I is equal to beta 2 sin theta r, or theta t in fact. So theta I equal to theta r. So if I replace this theta r with theta I, that means this will become theta I. And now you can see that you have to write in the next step, this should be written as theta r, and in the next step remove this theta r as theta I, then I am changing it here because I am having less space. Now, if you see that this is x beta 1 sin theta I, this is x beta 1 sin theta I, so this exponential term we can take common. So, we are having e to the power minus j x beta 1 sin theta I common. In bracket, we are having ei naught cos theta I plus er naught cos theta r. And here we are having e to the power minus j x beta 2 sin theta t and et0 cos theta t. And after this step also, this theta r should be replaced by theta I. So, in the next step, this is also replaced by theta I. So, now you can see that this is a relation which is true for any type of polarization. Beta 1 sin theta I is equal to beta 2 sin theta t. So, beta 1 sin theta I is equal to beta 2 sin theta t. So, this exponential term will get cancelled. And this cos theta I is common, so we can divide it here. Hence, we get ei0 plus er0 equal to cos theta t divided by cos theta I and here et0. Now, if I divide it by ei0, then it would be 1 plus er0 divided by ei0 equal to cos theta t divided by cos theta I et0 divided by ei0. So, this is the equation. This is our HI, HIS. This we have to use, that's why I am not clearing it. Okay. So, this is let us say equation number 7. Equation number 7. Now, we have to apply another boundary condition, and that boundary condition is for the magnetic field. The boundary condition is that at z equal to 0, both are having the tangential component equal. So, now let us write at z equal to 0, again at z equal to 0, this ht1 should be equal to his at z equal to 0 and hrs at z equal to 0. So, his at z equal to 0, so what is this? At z equal to 0, this term will be, you can write, this would be at z equal to 0, you can write from here. See the equation number 2. Equation number 2 and substitute z equal to 0, and it is only having the tangential component. So, ei0 divided by eta 1. So, this is ei0 divided by eta 1 cos theta I e to the power minus j, and the remaining thing is same, the first part. Now, for the reflected wave, so for the reflected wave we are having equation number 4. Substitute z equal to 0, it is 0. It is having the minus sign. So, minus er0 divided by eta 1. So, here we will have minus er0 divided by eta 1. There is no cos and sine, okay. So, there is no cos or sine. So, here this cos will not be present, and here also this cos will not be present, and this will be the equation. Now, for the transmitted wave, H1, it is H1, this is H2, okay. This is actually HT1, that is for tangential, and this is HT2 for the tangential, not for transmitted. So, HTS at z equal to 0. So, this is ET0. You can see from the equation number 6. You can see from the equation number 6, this is the transmitted wave, and z equal to 0 we have to put. So, z equal to 0, this term will vanish, and we get ET0 divided by eta 2 only, and e to the power x beta 2 sin theta t. So, the cos term will not be present here, and e to the power minus j x beta 2 sin theta t. So, this is the equation. So, this equation and this equation should also be equal. Now, we can clear it. We have used all the equation now. Now, we can clear it. So, this equation number, after this boundary condition, we have got the equation, and from there we will get another equation. Let's write that HT1 equal to HT2. This is HT1. So HT1 is EI0 divided by eta 1, EI0 divided by eta 1, e to the power minus j x beta 1 sin theta I minus ER0 divided by eta 1 e to the power minus j x beta 1 sin theta r equal to ET0 divided by eta 1 e to the power minus j x beta 2 sin theta t. This is the equation. Okay. Now you have got all the equations, and you have to do the same thing, that you have to replace this theta r by theta I in the next step. So I am having space here, so I am writing each and every line. E to the power minus j x beta 1 sin theta I minus ER0 divided by eta 1 e to the power minus j x beta 1 sin theta I equal to ET0 divided by eta 2 should be there. Yes, it should be eta 2. Eta 2 e to the power minus j x beta 2 sin theta t. Now we know that this beta 1 sin theta I is equal to beta 2 sin theta t. So if you take this common, then we get e to the power minus j x beta 1 sin theta I is common, divided by eta 1. We will left with EI0 minus ER0, here ET0 divided by eta 2 e to the power minus j x beta 2 sin theta t. And this exponential term will get cancelled because both are equal. Beta 1 sin theta is equal to beta 2 sin theta t. And if I divide it by EI0 and if I cross multiply this eta 1, then it is EI0 divided by EI0 minus ER0 divided by EI0. It is ET0 divided by EI0 and eta 1 divided by eta 2. So this is 1 minus ER0 divided by EI0 equal to ET0 divided by EI0 into eta 1 divided by eta 2. This is equation number 8. So now we will use the equation number 7 and 8 to define the reflection coefficient and transmission coefficient. So I am clearing all the part because I have used all the thing. Now we will derive the equation of reflection coefficient and transmission coefficient.